Hello everyone, we're Team 19 for Embedded System Design, ECE 4534. This is fall 2018 and we're in Dr. Plasmick's class. My name is Sajid.
I'm Thomas. I'm Alex.
And I'm Sasha, and our project's called Rover Tic-Tac-Toe.
Our project is a twist on the traditional game of tic-tac-toe. Instead of manually drawing X's and O's on the tic-tac-toe board, a rover will autonomously navigate the board and draw the player's symbols for the selected move using a dry erase marker held by a robotic arm. We use a pressure sensor grid on the board to determine the location of the rover. Our application allows for 1 or 2 players to play the tic-tac-toe game at once. A user playing in one-player mode has 2 options for the computer player's difficulty. We have an easy mode and a hard mode. Our application also visibly shows the users the location of the rover as it navigates the board. And we have a hidden surprise for a victorious user at the end of the game.
There were 2 types of constraints for our project, the ones given to us by the course specification and the ones that we set as project requirements. The ones in the course specification included the following. We had a budget of $400 to buy all necessary hardware and materials. Some of the hardware requirements included that the system had to use PIC32 microcontrollers as the processors, that provided Zumo motors to allow the rover to move, and a robotic arm costing less than $75 to perform a certain action. Additionally, the system could not use a line follower array or an overhead camera. Our final implementation met all of these constraints. The requirements that we set for our project were the following. The playing field would consist of a 38.1 cm by 38.1 cm tic-tac-toe board. The system would function such that the user would select a move through a graphical user interface, and a rover with a robotic arm would move around the game board to draw X's and O's. These tokens had to be drawn such that the X's were at least 4 cm long and the O's were at least 4 cm in diameter. Additionally, the tokens had to be completely drawn in the target squares. This last constraint of drawing the tokens fully inside the target squares was not consistently met, as the navigation was not 100% consistent and robust. This will be discussed later. The rest of the constraints were met through the various system components, which will be discussed now.
To meet our project requirements, we needed a robotic arm large enough to hold a dry erase marker with 3 degrees of freedom and a price point of less than $75. After doing some comparison shopping, we settled on the 4-servo Arm Uno 2.0. This large, composite wood arm met all of our project specifications at a price point of only $40. After purchasing the arm, an ARM control library was written. This library uses the output compare pins on the PIC32 to create a 20 millisecond period pulse width modulated signal for each of the 3 base ARM servos. By adjusting the PWM positive widths, each of the servos could be set to a specific desired angle. An API to perform complex motions over time was also created, which leverages the lower level ARM library. In a complex motion, each of the servo angles is updated every 60 milliseconds over the duration of the motion to give the arm a smooth motion path without any jerky movement. To allow integration with the final project, complex motions to draw X and draw O had to be created. The movements to draw X and O are defined as a sequence of arm positions and the transition speeds between those positions. In addition, a thread to allow commands to be sent to the arm from other threads on the same PIC was created. This thread receives a command message, like draw X or set servo angle, into its thread safe queue and sends an acknowledge message back once it is done with the action, as shown in the diagram on the right.
The motors are what allowed the rover to move around the playing field so that the tokens could be drawn in the correct tic-tac-toe squares. For ease of integration, motor control was abstracted away by an API which allowed the following commands: moving the rover forwards and backwards a given distance, turning the rover left and right a given angle, and asynchronously stopping the motors during a movement. Additionally, the motor control read encoder values to calculate distances and angles, and incorporated a PID feedback control loop. The motor control implementation was given in the motor thread. As indicated in the task diagram on the right, the motor thread interacted with the rest of the system in the following ways. The motor thread would receive movement commands from the navigation thread and controlled the motors accordingly. The motor thread would receive timer messages, which were driven by a software timer, every 100 milliseconds to indicate that the encoder values had to be read. When the encoder values were read, the PWM signals driving the motors were adjusted according to the PID feedback control loop. Lastly, the motor thread sent acknowledge messages back to the navigation thread when movements were complete.
Based on project specifications, we were unable to use the line follower array or overhead camera for rover navigation on our game board. To autonomously navigate the board, we used force-sensitive resistors to determine the rover's location. In total, 10 sensors were placed in a grid format around the game board. Each sensor has 2 pins. One is connected to the PIC's 5-volt input, and the other to a pull-down resistor, which is connected to ground. The connection point between the pull-down resistor and the force-sensitive resistor is then wired to one of the analog inputs on the PIC. The sensor's resistance is based on the amount of pressure applied to them. So when the rover drives on top of one of the sensors, the resistance will decrease, which in turn increases the analog to digital converter's reading. The analog to digital converter was configured to support multiple analog input readings using ADC scan mode. On the software side of the force-sensitive sensors, we created a sensor thread. On startup, the analog to digital converter interrupt will run a calibration routine that will take 2 readings of each of the 10 analog pins. The 2 readings for each pin is then averaged together, and the average value for that pin is then stored in an array. The average value for each pin will serve as a threshold comparison value that will be used in the conversion function. This conversion function is also called in the interrupt. It takes the threshold value array as an input and returns a 10-bit value as an output. Each bit in the integer value corresponds to a specific sensor on the game board. In the conversion function, the value of each analog pin is compared to the corresponding threshold value in the array, and if the pin's value is greater than the threshold, this indicates that the sensor has pressure on it. The corresponding bit in the 10-bit integer value is then converted to a 1. If there is no pressure, the corresponding bit value will remain a 0. This 10-bit value is then returned, and the value is sent to the sensor queue. In the main function of the program, the value is then added to a JSON post message which is sent to the server and stored in the database every half second. The communication for the project is done through a Raspberry Pi HTTP server. The Raspberry Pi is configured as an access point that will allow external devices like the PICs and the GUI client to connect to the server. The server is a Python-based HTTP server that uses multi-threading to handle multiple requests from different clients. The server receives post requests from the navigation thread and the sensor thread. The data from each thread is then stored in a MongoDB database. The GUI client and the navigation thread both send GET requests, and a specific JSON formatted message is then sent to each client, with the corresponding information from the database.
Once a game is started, the gameplay GUI will load. The tic-tac-toe board on the left shows the current board state and allows entry of human player moves when it is their turn. Underneath the board, the game status text box shows information about the current game state, and the server status text box shows information about the current server connection. The grid on the right represents the force-sensitive resistor array and shows their values in real time. Red indicates that the FSR is being depressed, while black indicates that it is not. In addition, the rover image on the board shows the current rover position on the FSRs as reported by the navigation thread.
Once the gameplay GUI updates the database with a move, the navigation algorithm kicks in. There are three parts to this algorithm: the direction determining function, the mapping state machine, and the command function. Upon startup, the rover must be placed in the bottom left corner facing towards the right to meet initialization criteria. From here, the mapping state machine is called. This state machine uses the force-sensitive resistor input given to the PIC by the server to switch states. Each state corresponds to a different position on the game board. Once a move has been delivered to the PIC from the server, this function calls the direction function. The direction function has three outputs: clockwise, counterclockwise, and stop. The direction function uses the current location and the next square to navigate towards to determine the optimal direction of travel. When this function outputs a direction, the mapping state machine can then send commands to the motors to correct for error that are detected on the FSRs, and when this function outputs a stop command, it allows the command function to know when to send a draw command. The command function is the last of the navigation algorithm's fundamental parts. Using the output of the direction state machine position function and the input from the server, this function sends the proper series of commands to the motors and arm. The vast majority of commands were sent to the motor. The commands sent to the motors were determined in one of two ways. Either a set distance to travel was sent, in which case the command function would spin waiting for an acknowledge message, or a message to drive a short distance was sent repetitively until the FSR array indicated otherwise. The commands to drive a set distance were usually implemented to navigate around a corner or to a line beside a square where the FSRs couldn't supply accurate enough information to draw. The short repetitive commands were used for the bulk of the navigation. The slow speed of travel allowed the FSR array to inform the rover when to stop, turn, send a set distance drive command, or allow the rover to correct its trajectory, whereas the set distance driving could throw the rover off the sensors. After the rover found its way beside the target square, this function would send a draw X or draw O command to the arm and wait for an acknowledge message before sending an acknowledge message of its own to the server, allowing the server to send it another move command.
To test and evaluate our project reliability, we played through multiple games of tic-tac-toe in all three play modes. In each mode, different move combinations were tested to validate how reliably the rover could navigate to each board tile. To facilitate software stability and reliability, all server communication was done using HTTP messages with JSON data bodies. Our protocol was designed in such a way that no single message between the server and the PIC is critical and will result in project failure if it does not send or receive. On the PIC side, we used the same data structure and queue functions for communication between all threads. This proved to be very consistent without failure or deadlock risk. The main software reliability issue which we encountered was from the use of the Python-based HTTP server library. During testing, we had an intermittent issue where the server would partially lock up and need to be restarted. This issue occurred on average slightly less than once per game, but is definitely an issue which would have to be addressed for a production-level project. From a hardware perspective, significantly more testing would be needed to get to 100% reliability in board navigation. The major issue which we encountered was in turning around corners. The combination of high latency between the sensor PIC and the rover PIC combined with the uneven board structure led to a diminished turning accuracy for the rover. In addition, extensive testing of the ARM draw X and draw O commands caused degradation in the servos over time. The arm gradually lost its ability to actuate to the necessary angles and would stall out. This issue could be fixed by simply using higher quality servos.
Robustness, or handling under extreme situations, is important to the success of a real-world system. As you can see in the GIF, even when the rover is angled horribly wrong, it still possesses the capability to correct itself back on track. During testing, when we would place the rover on the board at an angle, we noticed overcorrection was a prominent issue. To counteract this problem, we instituted a limitation on the number of correction commands that could be sent during a 5-second time interval. A drawback in the implementation of our system was we were only able to send the proper correction commands when the rover's right tread depressed the outer resistor and when its left tread depressed the inner resistor. If the rover managed to completely cross over one of these resistors, the commands to correct itself would only throw it further off track and require a manual reset. This situation could occur after a set drive distance command was sent or if the server failed to send FSR data in a timely manner. During testing, the ARM reliably drew the X and O symbols every time the command was sent. The ARM's only issue was the aforementioned server degrading through rigorous testing. In our physical implementation, it turned out that the rover would always drift ever so slightly left into the center of the board, so when the rover became offset with the left tread between the two outer resistors, it would reliably correct itself back on track.